All right, so today we're going to do the alternating series test, which you guessed it is for an alternating series. So for alternating series, either the odd terms are odd, or excuse me, the odd terms are obviously odd, negative, which means you would have a -1 to the n in there somewhere. That would cause all of the odd terms to be negative. Or your even terms are negative, which means you would have a -1 to the n plus 1 somewhere in there. But if you see one of those, what it means is the terms alternate, positive, negative, positive, negative, positive, negative. So they're easy to identify because if it has that in it, then it alternates. So actually, this is kind of like one of the tests I like a little bit better because it's easy to identify when to use it. Because some of the other ones, it's like, oh, when am I going to use this test and when am I going to use that one? This one's really easy to identify. It's when it's alternating. So for the alternating series test, first, make sure the series is alternating. I know that that sounds kind of silly, but just to be clear, you can't use this test for series that aren't alternating. Okay, so make sure that it is. And then here's the two parts to it. The limit as n goes to infinity has to be 0. And when you do that limit, you leave off the -1 part, like you leave off the fact that it's alternating. It's just limit as n goes to infinity, that has to go to 0. And that's kind of like the nth term test. You know, when you do the nth term test and it comes out to 0, you get no conclusion, like it might converge or it might diverge. And that's why there's another part to it. Your absolute value, and the reason you have to absolute value is because the terms alternate. The a sub n plus 1, so the n plus 1th term has to be smaller than the nth term for all n. Basically, the terms have to keep getting, the absolute value of the terms have to keep getting smaller. Now, just as a side note, it could still converge even if number 3 is not true. It could still converge. You would just have to use a different test other than the alternating series test. This test wouldn't prove it, but it might still converge and you could use like the integral test or something else to prove it. So just because this test doesn't prove it doesn't mean it doesn't converge. You just might have to use something else. All right, so let's try a couple of these. I'm going to do these and then give you guys a couple to try because there's actually not much to this. Do you notice that it alternates? You see that -1 in there? Okay, that's like the first step, like identifying that this is the test you're going to use. And so we're going to do limit as n goes to infinity of 1 over n. Again, it's like the absolute value of that. You would just leave off the alternating part. So hey guys, what is that limit going to go to? 0. We're on our way. All right, then you're going to plug in n plus 1. So if you plug in n plus 1 for n right there, you would get 1 over n plus 1. And is that less than or equal to 1 over n? That's the question. Is that true? Yes. If it has a bigger denominator, it's the smaller fraction, like a 1/4 is smaller than a 1/3 kind of thing. So that is true for n bigger than 1. And it doesn't really matter where it starts. It's just this one started at 1 something for n bigger than 1. So we conclude this converges by the alternating series test. And you can just write AST. It's kind of like, you remember when we did mean value theorem and you can write MVT for mean value theorem? Same thing, just alternating series test. That's like an understood abbreviation for that. Let's try another one. We're going to do limit as n goes to infinity of 1 over 3 to the n. So what is that going to go to? 0. Yay, we're good so far. So then you're going to plug in n plus 1. So 1 over 3 to the power n plus 1. Is that less than or equal to 1 over 3 to the n? Is that true? Yes, because the bigger denominator means the smaller fraction. So this is true for n bigger than 1 And so again, this converges by the alternating series test. And if at this point you're like, that's it, good, yes, that's it. This is one of the easier tests. Let's try another one. Limit as n goes to infinity, n over ln of n plus 1. So in the numerator, you got n. That's a polynomial, like n to the first, n to the second, n to the third, n to the fourth. That's a polynomial. In the denominator, you have a logarithm. A polynomial is going to grow faster than a logarithm. So this is going to keep getting bigger and bigger and bigger and bigger and bigger. And so this limit goes where? Infinity. Just to review, like the order of like what's more powerful than what. A factorial is going to beat an exponential, which is going to beat a polynomial, which is going to beat a logarithmic graph. So it's factorial, exponential, polynomial, logarithmic. But anyway, since this went to infinity, what's going to be our conclusion? It diverges, but not by the alternating series test. We weren't even able to get to the third step. It diverges by what test? Nth term test. So if it diverges, it just turns into an nth term test. So see how we have all this space over here? I'm going to give you guys a couple to try together, and you can talk to each other and work together, and then I'll go over them. But I just want to give you guys a couple to try. All right, so for this one, it's alternating because of the -1 to the n plus 1 there. So we're going to do limit as n goes to infinity of n over 2 to the power n plus 1. So what does that go to? Because technically it's the absolute value of that. You're just trying to show that it will end up at 0. So is that going to go to 0? Yes, because this is exponential, so the denominator is going to grow larger and larger and larger. So it'll go to 0. Now we're going to plug in n plus 1. So we will have n plus 1 over 2 to the power n plus 2, because it's n plus 1 plus 1. So is that smaller than n over 2 to the n plus 1, which is, bless you, which is just what you have there. And yes, it would be, because if you have the bigger denominator, I can't talk. The larger denominator is the smaller fraction. So that is going to be true for n greater than or equal to 1. And so what's our big conclusion to the whole thing? Good. All right, and then this one, we're going to do limit as n goes to infinity, n plus 1 over n. What did you guys get for that one? What will that limit go to? 1. Good. Why 1? Because that's correct. Yeah, those are the same. So you use the coefficient. It's tricky because they're not written though, but 1 over 1 is 1. If it comes out to anything that's not 0, then it is diverges by nth term test. Good. Right, you can't prove that it diverges using alternating series test. That only proves that it does converge. So if it diverges, you would say by nth term test, if that comes out to anything that's not 0. So essentially you're doing an nth term test is what this step is, and showing that that came out to no conclusion. And then if this is also true, then you get to make a conclusion. Good. Yeah, I think there's one on the homework like that. And I had put a sticky note on here of a couple I was going to actually get you started on to talk about that. And not tell you the answer, but give you a hint. But yeah, that can happen where even though this isn't true, it can still actually converge, which is weird. All right, do you guys need a break or do you want me to go ahead and just finish? Did I? Okay, so now we're going to look at this alternating series remainder error bound. I'm going to give you a lot of vocabulary and then kind of sum it up. It's going to sound bad because there's like a lot of vocabulary to it, but it's really actually not that bad. This is used to approximate the sum of the series. And this is what you guys were kind of asking about last week, because what we're saying is, does it converge or does it diverge? We're not actually well, for geometric, we find the answer because we have a handy little formula for that. But for most of the other ones, we're just saying, yes, it converges or no, it diverges. But what's the actual sum? This is a way that you can approximate it if it's an alternating series. All right, so again, this is going to look like vocabulary overload, but let me say what it all means and then we'll kind of sum it up. It's not actually that scary. It's going to look like a lot of them. So, all right, so we have R sub n. That's the remainder after n terms, or like the error, like the remainder is what's left over. So that's the remainder or the error after n terms. So the true answer would be adding up for infinitely, right? Like forever. But if you only add up like 6 terms, this is what's left over, like the difference between the true actual answer and your partial sum. Does that make sense? Like you have adding up infinitely and you have adding up for like, I don't know, 6 terms, and it's the difference between them. So it would be the difference between those. So capital S, that's like the true actual answer. So the actual sum, like if you could add up infinitely, and S sub n is the partial sum of n terms. So like if n was 5, it would be you added up the first 5 terms. So what this error bound says is that error, like the difference between those, what's left over, is going to be less than or equal to the n plus 1th term. So that's what this is, the n plus 1th term. So if you add up 5 terms, the error from that and the true answer will be smaller than the 6th term. And because the terms keep getting smaller and smaller and smaller, the more of them you add together, the more accurate your answer will be. And you can actually get it to be pretty accurate. So again, I realize that was a lot of vocabulary. Here's the main takeaway, the like too long didn't read version. The error is smaller than the n plus 1th term. So your error is always going to be less than or equal to, but the error, the amount that you're off by, will be smaller than the next term. So again, if you add up 5 terms, your error will be smaller than the 6th term. So let's try this, and the decimals get weird, which is why you get a calculator. All right, approximate this sum using the first 6 terms. So let's list out the first 6 terms. If you plug in 1, well, actually, first let's start with this. If you plug in 1, are you going to get a positive or a negative answer, or like term? Positive, good, because 1 plus 1 would be 2, squared would be positive. All right, plugging in 1 factorial is 1, so you just get 1. Now, if that term was positive, that means the next one is going to be negative. And so what I would encourage you to do is just sort of ignore this part. We already decided the first one's positive, the next one's going to be negative. It's going to alternate. It's an alternating series, so you can kind of ignore that. All right, if you plug in 2, what are you going to get? 1/2, good. And then the next term will be positive. If you plug in 3 factorial, 6, so 1/6. And then the next one will be negative. 1/4 factorial is 24. And then 5 factorial is 120. Those are the, I don't memorize them any further than that. That's what I have memorized, but 1, 2, 3, 4, 5. We want to do another one. So 6 factorial, 720. Wait, now I'm second guessing myself. 720, okay. So that's 6 terms, 1, 2, 3, 4, 5, 6. Okay, what you want to do is add those up. That is capital S sub 6. Here, you know what, let me write that out. We're summing up the first 6 terms. And be careful because every other one is negative, but go ahead and use your calculator and add that together. I know this is the hardest part, right? Like typing it in. I really don't like calculator problems. If you hit one button wrong, it's going to be wrong. And when you get the answer, hit math, enter, and it'll turn it back into a fraction, because that way we won't have to like truncate the number. It's 91 over 144. Well, try again. Be patient. All right, so that is this right here. That's our partial sum, but it's not the true answer, because the true answer would be if you were able to add up forever and ever and ever. So we have absolute value of whatever the true answer is minus this 91 over 144. That has to be smaller than the next term, which would be which term? The seventh, because we added up 6. So let's figure out what the 7th term is. Our error is going to be smaller than that. And again, if you add up a whole lot of terms, like I had us do 6, this is kind of a lot. The further out you go, you'll see it comes out pretty accurate. All right, so the 7th term, 1 over 7 factorial. I do not know 7 factorial off the top. 5,040. So our error is going to be smaller than 1 over 5,040. Like it's going to be really close to the true answer. Now, if you recall from Algebra 2, and I know you probably don't, because Algebra 2 was like a lot of years ago for a lot of you, but when you do absolute value problems, it splits into 2, the positive and the negative. Oh, head's nodding. Okay, good. Positive and negative. So the first one's going to look just like that. You'll have S minus 91 over 144 less than or equal to 1 over 5,040. If you're like, hey, it looks like you just recopied it. Yep, sure did. That's it. But then for the other version, do you remember what you do? Because there's 2 things you do. You switch the sign, good, and then make it negative. Now here's where we'll go to decimals, because we'll be down to like our final answer here. So for this one, you would add over the 91 over 144. So go ahead and add those together in your calculator. You would have 1 over 5,040 plus 91 over 144. And we'll do a decimal again, because we're getting down to like the final answer here. So you're adding this to the other side. So you would just add those 2 awful looking fractions together. Now, I know we usually do 3 decimal points, but I had us go out pretty far for this one. It's going to be really accurate. Let's do 5 decimal points, okay? Because it's going to be pretty accurate. I think the first 3 are almost the same. Did you get 0.63214? Okay. And then for this one, you're going to do negative 1 over 5,040 plus 91 over 144. So you're adding this to the other side. It's just you would have a negative in front of that. What I would do is go back and just insert a negative into that, but you can retype it if you want to, like whatever floats. Okay. 0.63174. So here's the final answer. Our true sum, if you could add up the terms infinitely, will be in between those 2 decimals. So 0.63174 and 0.63214. So that's pretty accurate, isn't it? I mean, I guess you could disagree, be like, no, I want it more accurate, but I think that's pretty good. So yeah, you can get a pretty good estimation of using that. Number 5, we're not doing that. It says, how many terms would you have to go out to make sure your error is smaller than 0.001? Now for this one, we went out 6 terms, and so our error was smaller than the 7th term. So we want our error less than 0.001. That's for the n plus 1th term. So if you plug in n plus 1, that needs to be smaller than 0.001. Like we want it to be smaller than that. So if you plug in n plus 1, you're going to get 1 over n plus 1 to the 4th. We want that to be smaller than 0.001. So again, your error is the smaller than the n plus 1th term. It's like the next term. So it's easily said. And then we have like all the algebra of working this out. This one's just going to be a lot of algebra. What would you do to both sides? Yeah, and I would also write this as a fraction. What would that be in fraction form? 1 over 1,000. Good. So we have 1 less than or equal to 1/1000th times n plus 1 to the 4th. The reason I wrote it like that is I think it makes it easier to see this, because then you would multiply both sides by 1,000. And this next step is personal preference, but does anyone like to have the variable on the left side, like when you're solving something, like because we read left to right? I don't know. I'm going to flip it around. That you don't have to. That's just me. N plus 1 to the 4th would be greater than or equal to 1,000. I just wrote it the other way. You don't have to do it. All right, and then what would you do to both sides? You have to get rid of 4th root. And don't worry, we're going to have a calculator, so hold on. And then last step. Not add 1, but yeah, good. Subtract 1. All right, so here's what you want to type in. 4th root of 1,000 minus 1. Do you guys remember how to do a 4th root? Yeah, it's in the math menu. Well, I think you have to hit 4 first, or you might not have to. I don't know. Anyway, math menu, it's the xth root. 4th root of 1,000 and then minus 1. .623. So how many terms will it take to ensure that your error is less than 1/1000th? You have to go to the next one, so 5 terms. So it will take at least 5 terms to get the error small enough. And again, the more terms you do, the better your approximation. So the more you do, the closer you're going to get it to the true answer, the more accurate.